Hello, everyone. My name is Huaishu Peng. I'm from Cornell University, and it's my pleasure to be here to present our novel 3D printer that can print soft and interactive 3D objects directly from layers of fabric sheet. This work is done by a joint group of Jim Mankoff, Scott Hudson, and Jim McCann at Disney Research Pittsburgh. So we have seen a boost in the arena of 3D printing that empowers people to create customized 3D models on demand. From small goods like printed Yoda or octopus to large-scale creative things like aircraft engine or 3D printed buildings. People are also look into 3D printing in fashion and trying to print shoes or clothes, as I show in this example. However, the material widely used in 3D printing are generally limited to hard material like plastic or metal. Even the printed clothes I mentioned above are made with plastic with carefully designed pattern to support folding. Recently, soft object has been examined with several printable materials or printing technologies. For example, rubber-like materials such as UV-cured silicon or specially formulated Ninja flexible filament are also available for commercial 3D printers. Hudson also introduced soft prints with needle-felted yarn in last year's SIGCHI. However, the system I mentioned above or the material I mentioned above are limited either in resolution or lack of the variety of textures as in fabric. So talking about fabric, it is different from raw printing materials like plastic, powders, or silicon liquid. Fabric is available in a wide variety of colors, patterns, textures, and thicknesses, or they can even be conductive. So in this work, we make use of off-the-shelf fabric sheet as a printing material to automatically form 3D soft object. And because we can make use of conductive fabric sheet as a second printing material, we can even make 3D printed soft object be interactive. Conceptually, our 3D printer design is related to other layered printing technologies involving paper or metal. But because fabric is soft, it presents a unique set of handling and cutting challenges that we address in our design. So here is an overview of our printer structure. It consists of an inverted vacuum table for cutting, a bonding platform for gluing, a print head with a laser head at the top and a heating disk at the bottom. The print head can move within the XY platform for cut and glue, and the bonding platform can move along the Z-axis to transfer and stack cut profiles. This image is a close look of the print head with the laser head aiming to the top and the heating disk facing down to the bottom. For cutting, the laser cut used the laser beam from a 40-watt laser tube located at the back of the printer. This image just shows the laser tube at work, actually. Here is the image of the fabric sheet we are used in most of the examples. The fabric sheet is prepared with a layer of adhesive backing on the back of the fabric to allow for layer bonding. Now I'm going to show you how our fabric printer works. So before printing, the fabric roll is preloaded onto the vacuum cutting platform with a vacuum turns on. To start one layer, we move in the print head. And then we cut on top of the vacuum table. After cutting, we first move out the print head from the printing area. Then we raise the bonding platform to catch the newly cutted profile. Once the bonding platform reaches the top, the vacuum is off and the fabric plate is transferred to the bonding platform. We move into the print head again for layer bonding. There are a couple of design decisions we made lead to this printing process. First, for cutting, we use laser instead of a direct machining tool to avoid snag or deform of the fabric layers. Second, our use of the inverted cutting table and the raise of the building platform simplifies the fabric transfer from the top to the bottom to a single vertical motion. Here is how our printer actually works. The print starts with a sliced printed model. For each of the sliced layer, the laser cutter cuts the 2D contour of the shape of the fabric on the inverted vacuum table. The vacuum holds the fabric in place during cutting and also helps to remove smokes. Our printer cuts around the outside of the layer more than once to ensure a fully disconnection from the fabric roll. After one layer finished, we transfer the newly cut pattern to the building platform by raising the bonding platform all the way up to the top and turn off the vacuum. The newly cut layer then naturally transferred to the building platform. After the building platform moves back, the print head moves in again to activate the adhesive backing in order to firmly attach the fabric to the base or previous layer. First, corner of the stacks, then center of the edges, and finally the cutting profile. Fresh fabric is then rolled into the cutting area, and this process repeated for each layer of the model. The resulting object is a cube with layers of fabric, but the design object is already encapsulated into this. Once the print is complete, the support material is peeled away to reveal the finished object. This process is analog to the removal of support in the other 3D printing technologies. Here is our printing result, a soft and flexible Stanford bunny. Please notice that the overhung part of the bunny ears. Our method can successfully print complex structures as well as preserve the model details. The bunny above contains 32 layers of fabric sheet with a 2 mm thickness. The printing time for our Stanford bunny example is 2.5 hours. Now I'm going to show you a bit of other things we can do with our fabric printer, including manipulation deformation, dual material printing, printing sensor, and even printing circuit. Let's start with manipulate the model stiffness. This is done by embedding appropriate patterns of cut inside a solid print and leave the surface of the model intact. You can see from the image above, when the stack is bent, it's easier to bend from one direction rather than the other. In this wing example, the apex and the root of the wing are easier to bend vertically, while the middle part of the wing is more easier to bend horizontally. Notice that the manipulation is hidden inside the interior and does not affect the outside of the object. Here's a closer look of how the pattern oriented inside the model. Our printer supports one print work with a second layer of fabric material. With this, we can produce 3D objects with additional variations. As you can see in the image above, different layers of material can be loaded onto the cutting bed from 2 different directions orthogonal to each other. Before printing, a window the same size of the bonding box is cut in both materials. Then during printing, only the material to be used in the next layer is advanced. When the layer moves to the stack, a bonding cut its bonding cut becomes a window in the material, and this process can be repeated. Here is an example that we did with the dual material printing ability. Notice that the draping effect in this example, this is impossible to achieve with most of the other printing technology. With the second layer of the material loaded with conductive fabric sheet, we can even make the soft print interactive. In this example, we add one layer of conductive fabric sheet in between the normal fabric casing and created the printed soft button. Here's another example of a soft slider printed with our printer. Finally, we can also print soft circuit embedded into two different layers. This provides potential opportunities for us to print soft objects with electrical functional features. To join circuitries located at different layers and avoid short, we cut holes on the non-conductive layer to allow the heating disk to go through this hole to make the top conductive layer bonded to the lower conductive layer. Here is animation illustrate the process. The bottom layer is the first conductive circuit layer. We then print the second layer with a non-conductive fabric with a hole the same size of the heating disk. We then pause the printer for a moment to remove the cutout to reveal the bottom conductive fabric. We then print the top layer as a second layer of the conductive circuit. We finally order the heating disk to press through this hole to make the two conductive layers attach to each other. Using this method, we have successfully printed a coil with two circuit layers that joins through this printed via. Here, the coil works as an antenna that can harvest electricity wireless from a cell phone's NFC to blink the LED. The printed cell phone case is soft with electricity functionality. So far, we have demonstrated our novice fabric printer prototype and the potential soft and interactive prints empowered with our solution. Obviously, our first working prototype has many parts that can be improved in the future. For example, the bonding method for our current printer uses a heating disk. In the future, we are thinking to improve this heating disk with a steaming head to accelerate the printing time as well as reinforce the gluing effect. Printing time in our current printing design is limited by our bonding method as well as the moving time of the bonding platform. The bonding time can be improved with the method I just mentioned above. And in addition, it should be possible to substantially increase the vertical speed of the bonding platform using a large motor or a driving train that is geared more aggressively. In this work, we have presented a new type of layered-based 3D fabric printer that can form precise yet deformable 3D objects from rolls of off-the-shelf fabric. Our printer supports the use of two different fabric types in one print, allows a number of additional features to be included in prints, such as print soft compactive sensors or soft circuits. And I'm now ready for questions, and thank you very much. By the way, sorry, I have the fabric bunny with me, and if you want to have a look, you can. I'll do it later.
So we've got lots of time for questions yet, so just come up to the microphone.
Hi, that was a really great presentation. Jennifer Jacobs, I'm from the MIT Media Lab. It seems like because you're adding additive fabrication processes with the subtractive process, you end up having a lot of waste material left over, depending on even if you're printing very small parts. Do you have any thoughts how to move forward in this work with potentially less waste material or ways to reduce that?
Thanks. I think this is a really nice question. And frankly speaking, we didn't consider this when we're doing this printer because it's like the first working prototype. But thinking about the waste of the material, I think one possible solution is like to have more printing the object within one cube so that it can save the materials. I think it's similar to like some of the other type of 3D printers that you have to have this support cube outside there. I think it's similar. And to save the material, you can have multiple things print at once, things like that.
Thank you.
Thanks.
Hi, Melody Vidal from Lancaster University. Thank you for a great talk and great project. I'm just wondering whether you have had fire hazards by laser cutting the fabric and whether you have tested different kinds of fabric and found that some work better than others.
That's really considerable thought. Actually, when we designed this printer, I have a fire extinguisher just sit next to me. And thankfully, I didn't get the chance to use that. So no, we don't have any fire event, I guess because of we have this vacuum table that keeps sucking the airs and smokes from the top, so that lowers the chance for this fire effect. And I think this is the prototype, and if we develop that into a real product, we'll have a more careful design of the mechanical part and the casing to prevent things like that. Thanks.
Thank you.
Hey, this is Lining, also from MIT Media Lab. I just, inspired by your talk, I just have this random idea. Maybe for fabric printing, you can also printing thread directly. So you can write things with thread. But maybe you can also have like a specific customized thread with adhesive or thermal adhesive or something with a hot plate under it. Just random.
I think we should collaborate together.
Any more questions? So what was the biggest challenge in the implementation? Like, what was the hardest part? Like,
fire control? No, I mean, so I guess to have the plan to make the whole design process work, that with the inverted vacuum table to work, that is the biggest challenge when we have this fabric printer designed. Yeah.
thank you.